demonstrated that there are n plus 1 points on every single line but L1. So since L2 is not L1, then we have already shown that L2 has exactly n plus 1 points. Why? Well, because L2 was one of the lines that doesn't go through P1. In fact, it doesn't go through P1 or P2. And so, okay, so L2 has exactly n plus 1 points on it. So what? Well, if this line L2 has exactly n plus 1 points on it, now I reach for my point that is off that line, x. And what can I say about x? Yeah, by lemma 8.4, don't remember, probably A, since x is not on L2, and L2 has n plus 1 points on it, then there are n plus 1 lines through x. Okay, well, if there are n plus 1 lines through x, now, believe it or not, we now re-invoke lemma 8.4b to say, but x is not on L1. So, by lemma 8.4b, if there are n plus 1 lines through x, then there must be exactly n plus 1 points on any line that doesn't go through x. There are n plus 1 points on L1. So, yo.
So why can't there be a line that goes from like one of the points on L2 to like P2 without going through x?
Wait, let me sort of retell the story in like pictures and hand waving, and then I'm going to answer your question. Okay, so it kind of started like this, man. There's this line L. There's exactly n plus 1 points on it. Where is this line L? I'm not sure. But I know it misses 2 of the core 4. So let's suppose that it misses P1 and P2. So where is this line? Somewhere, but it doesn't go through P1 or P2. Well, if it doesn't go through P1 or P2, then first, then as there are n plus 1 lines, can I just make more silly like attack stories? Right, there are these n plus 1 points on L, right? They're there. That was the only thing I know. But I know that this line P1 isn't on my line L. So the n plus 1 points on my line L attack P1. Okay, now P1 must have exactly n plus 1 lines through it, because P1 was a point off of this line L. Then, the n plus 1 points on line L, my original assumption, again, since I know it doesn't go through P2, attacks P2. Now there are n plus 1 lines through P2. Okay, now that we know that, now take any other line whatsoever, calling it M temporarily, and suppose that M doesn't go through P1. Well, if M is off P1, then the n plus 1 lines through P1 attack M, making exactly n plus 1 points. So P1 attacks every line that doesn't go through P1. Similarly, P2 attacks any line that doesn't go through P2. And so every single possible line has been attacked by P1 and P2, except the one line that P1 and P2 can't attack, that neither of them can attack, the line that they are both on. Okay, so there's only line L1 left to be destroyed. Well, line L2 was a line already destroyed. It already has n plus 1 points on it. So now L2 attacks X, a point which we have proved to be both off L1 and off L2. Right? So now the n plus 1 points on L2 attack X, making their n plus 1 lines through X. And finally, X attacks L1 back. And the n plus 1 lines through X attack L1, making there be n plus 1 points on line L1. And that now covers every single line. Because every single line either misses P1 or misses P2 or just is line L1. Now, that was pretty clear, I think. Do you still have a question? Good. It's easier for me to just repeat myself than try to understand your question. All right, good. So we have that 1 implies 3. Now I shall invoke this pro move, which is to say, dude, by duality, this sort of like meta principle that points and lines are the same, have all the same relations in any finite projective plane model. We also have that 2 implies 4.
What?
Because literally it is the exact same proof. Are you okay with that?
Sure.
Yeah, it like just is, right? Now in the proof that 2 implies 4 is just that there's this point with n plus 1 lines on it, so now every point must have n plus 1 lines going through it. But the argument is exactly the same. Just with the points and lines like switched. Okay, cool. Okay, I'm going to sort of add now to the picture. Can you turn the camera for a second? And if also if everyone's cool with that, maybe we could, well, I don't know what board we're going to erase. But this was the hard part of the proof. So now we're back here. What have we shown? We've shown that 1 implies 2. We've shown that 1 implies 3. We've also now, sort of by invoking duality, shown that 2 implies 4. But of course, 3 just trivially implies 1, because if every line contains n plus 1 points, then of course there exists a line with n plus 1 points. So we're okay with that? So we do don't and don't. And okay, and now like I claim that all of 1, 2, 3, and 4 are now logically equivalent to each other, because say if you want to get to 4, you just go like, you know, 1 to 2 to 4, say. Are you with me? By the transitivity of the logical sort of implication relation. So since 1 implies 2 and 2 implies 4, 1 implies 4, and since 4 implies you just get them all, man. And to show that like 3 implies 4, for example, well, 3 implies 1, which implies 2, which implies 4. Cool? Say cool. And also 4 implies 3 because 4 implies 2, which implies 1, which implies 3. Okay, so the last thing left to do is to link all of this to 5 and 6. What does this extreme sort of symmetry tell us about the total number of points and lines? All right, there are 2 different proofs of this. There's like the Gossett proof, which is cool. Then this is sort of the Daniel Zhu proof, which I think is just better. I didn't write this down though. I think I get it. Goes something like this. I shall now show that 3 implies 5. Ready? Let's see if I can do this. All right. Suppose that every line contains n plus 1 points. All right. Well. Oh, notice, sorry, that though I am claiming to prove that 3 implies 5, like because I've shown that 1, 2, 3, and 4 are all logically equivalent, I really have like 3 and 4. Okay, so this is really like 3 and 4 imply 5, but that's the same thing as 3 implies 5 because I've already shown that 3 implies 4. Okay, so I know that every line contains n plus 1 points. Every point is on exactly n plus 1 lines. All right, so just take a point. Take a point P. All right, here's this point P. Here it is, just chilling here. All right, well, how many lines are there through P? Answer, there are exactly n plus 1 lines. So let's just, draw them all. N plus 1 lines, through P. And they're all distinct, these lines. And also, of course, none of these lines can intersect each other again anywhere else except for P. Cool? Okay, so these are lines L1, L2, L3, L4, all up to Ln plus 1. All right, well, how many points are there on these lines? Exactly n plus 1. So besides P, how many other points are there on each of these lines? N. And as these points are all distinct on any given line, these are all different points. And I'm not double counting any points because none of these lines can intersect anywhere else. And therefore, now let's just count all the points. Well, we have n plus 1 lines. How many points are there on each line, not counting P? N other points on each of the lines, plus 1 for P. Done. Pretty short, huh? Yeah, that's what happens when you let Daniel Zhu into your life. Suddenly you get really short, clear proofs. It's so obvious. It's so obvious that no one thought of this proof for the first 7 years I taught Discrete Math. But yeah, there it is, right? You just take any point, consider the n plus 1. I guess there might be more. Is there more justification that's needed that I'm sort of not missing any points? Let's talk that out. Why am I definitely not missing any points?
Because there's a line between all of
Oh, that was just a shrug of I don't know.
Right, and then for each line, it's just left.
And left. I know there can't be, here's my answer. I know there can't be any other points because there were just some other random point just chilling over here, then just no, man. Because there's a line through P at every point, right?
Yeah.
And so then there would be another line, but we've accounted for all the lines. We know there are exactly n plus 1 lines through P. So any point whatsoever which is not P, there's a line through P in that point. And as there are only exactly n plus 1 lines through P, then every point is accounted for, besides P. Cool? Okay, good. Is it worth our time to show that 3 and 4 implies 6? I think it might be worth it. Let's do it. Just take a minute. We could invoke duality, but the proof only takes a minute and it's a pretty picture. Why do 3 and 4 imply 6? Well, Courtney, can you take a picture of that board with my phone? Why do 3 and 4? Do you need to unlock the phone to take a picture or
No.
Well, the future. Why do 3 and 4 imply 6? Well, I don't know. What should I do? Oh, I know.
Take a line.
Take a line. Let this line be L. Note that there are exactly n plus 1 points on every line. So, over here. So it's P1, P2, P3, P4. Pn plus 1. And now, what else do I know?
Wait, no, I'm sorry, no, instead of phone.
Through each of these piece of i's, there are n plus 1 lines, and so we get a little bit of this action, yeah? And those lines are all distinct, and no 2 of these lines can intersect somewhere else, right? Because if two of these lines somehow met at some new point, then that would be just like a no, because, wait, why?
Wait, it definitely?
Oh no, they definitely do.
Yeah.
Take it back, sorry, that was nonsense what I said. What I meant to say was, no two of these lines can be the same line. What I meant to say. Why is that impossible? Because then you would have two different lines going through like P4 and Pn plus 1, right? So all these lines are different from each other, and so let's just count the lines. You know, there are n plus 1 points on L, and there are n lines not including L through each of the p sub I, and then you add in L, so it gives you n squared plus n plus 1 lines. And then a similar argument says, yo, there can't be any other lines that we like missed, because if there was some other line just chilling out here
They would have to intersect.
by FPP 2, it would have to meet L somewhere, but L would have to meet L at one of the points, but we've already accounted for every single one of the lines through all the points on L, so that's just all of them. Woo! Okay, so we have now showed that I'm just gonna, can I just kind of do like this basically? Alright, so now we have to do the last thing, which is if we're really trying to show that these are all equivalent to each other, we need to show that like 5 and 6 imply 1 or something like that. Okay, so this is the part I didn't fully prep, but I think I pretty much have it under control. So, show that 5 implies 1, say. Okay, how do I say this well? Okay, so here's what I'm going to do. Suppose there are n squared plus n plus 1 points. That's 5, well that's what 5 is. Show that there must exist a line with n plus 1 points. Wait, I think I need to cheat and look at the book for like 1 second. This is a very short proof. I just want to make sure I say it correctly. Good video. Yeah, where to go? Here it is.
It's the power of editing.
The power of, I don't edit because I'm lazy.
Do it.
Okay.
In your stacks borders.
Ah, okay. What? Okay. Alright.
We suppose points are the same.
So yeah, now I want to show what? Okay, good. Okay. So there exists a line with n plus 1 points. Okay, so I guess it's something like this. Okay. Why is this true? So great. I want to show that there's a line with n plus 1 points. All right. Well, suppose there's a line. Suppose we have a line L with m plus 1 points on it. All right. So just take here's the game. Here I got this now. Take an arbitrary line L. Suppose it has m plus 1 points. I claim it's sufficient if I can just show that m equals n, then I will have shown that there is a line with n plus 1 points. Okay, so why must m be n? Well, look, this is like some strange meta thing. I have a line with m plus 1 points on it. So P1, P2, P3, PM plus 1. Tell the entire story over again. Insert, so I'll just try like insert previous 1 hour. note that we have showed that 1 implies 2, and also that 1 implies 3, and also that 3 implies 5, and et cetera, et cetera, et cetera. And what is 5 is that there are n squared plus n plus 1 points. So what do we know? So we must have m squared plus m plus 1 points. But if we have n squared plus n plus 1 points, and also, okay, alright, so what do we know? N squared plus n plus 1 equals m squared plus m plus 1. Because, right? Gaussian now invokes calculus, believe it or not, to show that these two quadratics are increasing and therefore like don't intersect or some crap like that. But I think it's like prettier to just go like, how do I do this? I think if we do this, it's like prettier, right? So that's like n minus m, n plus m, plus n minus m. This is basically just silly. So this is n minus m, n plus 1, or some crap like that. Alright, so there are two options, man. N is m, that's the real option, or n plus m equals -1. Like, I don't think so. Conclusion, if this freaking model has n squared plus n plus 1 points, and m squared plus m plus 1 points, then n just equals m. Woo! N equals m, so what do I know about this line L? L has n plus 1 points on it. And so there is a line with m plus 1. There is a line with n plus 1 points on it, which is 1. Thus, 5 implies 1. And by duality, 6 implies 2. And thus, yeah, I think this is the way to do it. By duality, 6 implies 2. And then you can just get now that like 5 implies 6 as well, right? Because 5 implies 1, which implies 4, which implies 6, etc. So I now claim that we are done. That was like a little subtle at the end there, but is that good enough? I feel like that's good enough. Whew. You guys know Reynold? Last year he got so mad at this, he just kept fighting me until I